Welcome to AI Podcast. I'm David Chen. Today we're exploring a paper that blends behavioral economics with model alignment. The title is KTO, Model Alignment as Prospect Theoretic Optimization, led by Kawin Ethayarajh, with senior authors Douwe, Kiela, and Dan Jurafsky. The team spans Stanford University and contextual AI.
Hi, David. I'm Maya. That sounds intriguing. Can we start with the quick takeaway so listeners know the point right away?
Absolutely. TLDR, the authors reinterpret alignment losses through prospect theory, then introduce KTO, a training objective that learns from simple yes or no feedback on each output. Across multiple model sizes and data sets, KTO generally matches or beats strong preference-based methods, handles skewed data well, and sometimes works even without a supervised warm-up.
So, instead of asking people to compare two answers, we can just say this answer is good or this answer is not, and the model learns from that?
Exactly. That is the practical punchline. On authorship, again, the representative names are Kawin Ethayarajh, Douwe, Kiela, and Dan Jurafsky, and the work appeared at ICML 2024.
Great. Give us the background and the problem setup. What are they trying to fix?
Alignment often uses supervised fine-tuning and then methods like RLHF or DPO. Those rely on pairwise preference data, which is costly to collect at scale. The paper asks two things. First, why do these alignment losses work as well as they do? Second, do we really need preferences in pairs? Their lens is prospect theory, which says people judge outcomes relative to a reference point and feel losses more strongly than gains.
Right, that loss aversion idea. What was missing in prior approaches?
RLHF is powerful but operationally heavy and can be unstable. DPO is simpler but still needs pairs. Simple steering methods without a preference pipeline tend to trail in quality. The gap is clear. We want data that is cheaper to gather and a loss that embeds human-like judgment, without the overhead of pair construction.
Okay, so what is the core idea behind KTO, and why did the authors think it would work?
They define a family of human-aware losses that mirror human biases, such as reference dependence and loss aversion. From that family, they derive KTO. Picture three ingredients. 1. A reference model, usually the model before alignment. 2. A measure of how far the current model has moved from that reference. 3. A value function that says, improvements give diminishing returns while degradations hurt more. Then you label each output as desirable or undesirable, and the loss nudges probabilities in line with that value function. It's simple, and it matches how people tend to judge outcomes.
That makes sense. Any practical tricks that matter?
Yes. Computing the exact reference term can be expensive, so they use a small, efficient approximation inside each mini-batch and keep training stable by not backpropagating through that estimate. In practice, this keeps the method straightforward to run.
How did they test KTO against other methods?
They compared KTO with DPO and several baselines across a range of open model families, from small to large. Data sets covered helpfulness and harmlessness, as well as open-source conversational data. For evaluation, they used an automated judge to compare responses to a strong supervised baseline and also looked at task benchmarks to make sure general abilities did not regress. They ran stress tests too, like heavy label imbalance.
And what did they find in plain language?
First, losses that reflect prospect theory tend to outperform simple steering approaches. Second, KTO, using only binary feedback, often keeps up with or surpasses DPO across many setups. Third, it stays robust when positives are scarce, even when the dataset keeps only a small fraction of desirable examples. And when the base model is strong, KTO can work without a separate supervised warm-up, which saves time and data.
That is compelling, but let's be careful. Any caveats or concerns?
A few. Many headline comparisons rely on an automated judge, which correlates with human ratings, but is not a perfect substitute for diverse human evaluation. The reference term they estimate is intentionally approximate, which is efficient but introduces bias that could interact with batch composition. Also, the clearest gains tend to show up at moderate to larger model sizes. And when user preferences conflict, a method that follows the majority may need extra fairness constraints to avoid marginalizing minority views.
If I am a practitioner with a DPO setup today, how hard is it to try KTO?
It is not a heavy lift. The data requirement is lighter because single outputs with thumbs up or thumbs down are enough. Optimization is straightforward. If you already log simple approval signals, KTO fits that pipeline. It is still wise to A/B test in your environment, but the barrier to entry is low.
What tips would you pass along from the paper?
Start with a standard alignment learning rate and a micro-batch size that lets the reference estimate be defined. Keep the loss aversion weights balanced unless your labels are skewed, in which case tilt them slightly toward the scarce class. If your base model is capable, pilot KTO without a long supervised warm-up and check quality before adding more steps.
Where does this line of work go next?
Several directions. Use KTO in online settings where feedback streams in continuously. Extend the binary label to multiple objectives like helpfulness, safety, and style while keeping the prospect theory grounding. Improve how the reference point is estimated so it adapts without adding heavy compute. And complement automated judging with broader human panels, especially in safety-critical applications.
Let me try a one-sentence wrap. This paper reframes alignment through prospect theory and offers KTO, which learns from simple yes or no feedback. In studies across models and datasets, it often matches or beats preference-based training, stays stable under imbalance, and sometimes removes the need for a supervised warm-up with thoughtful caveats around evaluation, estimation, scale, and fairness.
Perfectly put. If you're weighing costly preference pairs against simpler feedback at scale, this gives a principled reason to try the simpler path with a loss that mirrors how people judge outcomes. Thanks for listening to AI Podcast. I'm David Chan.
And I'm Maya Patel. See you next time.